Hi everyone, I am Tanushree Kaushik. I will be engaging today's technique session organized by IEEE Computer Society. Our topic for today's session is searching algorithms. We're mainly going to be focusing on linear search, binary search, and ternary search. So let's begin. Before we start with searching algorithms, let's look at some basic definitions in data structures. Firstly, we have data, which is the most fundamental unit. They are values or sets of values. Then we have a data set, which is a unit, single unit of values containing data. So data items, which cannot be divided into sub-items, are known as elementary items. And the items which can be divided into sub-items are called groups. Then we have an entity. Entity is an attribute or a property to which we can assign values. We can assign either numeric or non-numeric values to these entities. A field is an elementary unit of information that represents an attribute. Now, record is a collection of field values of a given entity, and file is a collection of records of that particular entity in the entity set. So, with this basic knowledge, I think we can start with searching algorithms. So, the algorithms which are designed to check for an element or retrieve an element from any data structure where it is stored are known as searching algorithms. We can retrieve the index of the element through these algorithms. So these searching algorithms have been divided into two categories based on the type of search operation. Firstly, we have sequential search, where we traverse the data structure sequentially and every element is checked. Linear search is a type of sequential search. Then we have interval search, where the algorithms are designed for searching in sorted data structures. And these algorithms are more efficient as they repeatedly target the center and divide the search space in half or any more parts. Binary search and ternary search are interval searches. So now let's start with linear search. Linear search is the most basic and simple searching algorithm. This is used to return the particular element by checking the given collection one by one. So here we traverse the data structure sequentially. So if a match is found, that particular item or index of that element is returned. Or we continue the search until we reach the end of the collection. And if we still don't find a match, we return that the element is not present in the given data structure. So how linear search works is we consider every element as a potential match with the key, that is the required element, and check for the same. If we encounter an element equal to the key, then the search is successful and that element's index is returned. If no elements are found equal to the key after traversing through the entire data structure, we return that no match is found or that required element is not present in the data structure. So this is the algorithm of linear search. I've done the code in C. So what we do is first we have a flag which I've set to 0. Then we have an iterator I which is traversing through the array linearly. We check for each index as we check the array and check if it is equal to the element. Here element is the key which is the search element which we need. So if this is equal, we print that it is found as this position. We set the flag to 1 and break. And then we check if the flag is still 0, that means the element has not been found. Here I'm returning the position, which is index plus 1, or you can either return just the index of the search element. This is the algorithm for linear search. So we have this example here with the array, the size is 6, and here key, which is the element to be found, is 4. So firstly, we set flag to be 0, and then we have the iterator also starting from 0. For a of 0, which is 2, we check if 2 is equal to the key, which is not true. And then we go to the next element, a of 1, which is 1, not again equal to the key. We go to the next element, a of 2, which is 5. 5 again is not equal to the key. Next element, a of 3, 9 not equal to 4. And then we have a of 4, which is 4. Here we have key to be equal to a of 4. So we print that the element has been found. And then we set the flag to 1 and break out of the loop. This is how a linear search works. Some of the advantages of linear search is that it can be used irrespective of whether the array is sorted or not. We can use linear search on any type of array and arrays having any data type as well. We do not require any additional memory for linear search, and it's more suited for small data sets. Also, linear search has a few drawbacks. It has a time complexity of order of n, so it makes it slow for large data sets. Hence, it's not really suitable for large arrays. When we can use linear search is when we're dealing with a smaller data set. When we're searching for a data set stored in contiguous memory, linear search is very useful as well. This was about linear search. This is the most basic and simple algorithm. So now we can move on to some more complex one, binary search. Binary search is a fast search algorithm which works on the principle of divide and conquer. This searching algorithm only works on data in the sorted order. So for binary search, we need the array to be sorted. That is one requirement. And here we use the principle of divide and conquer in binary search. How does binary search work? We use the middle element for comparison to traverse the collection. So we check if the middle element matches the search, which is the key, then we return the index. If the middle element is greater than the key, we continue the search in the left subarray. And if the middle element is lesser than the key, then we go to the right array. We'll keep repeating this process until the size of the subarray is reduced to 0. So basically, in binary search, we divide this search space into two halves. We find a middle index, and divide the searching space into two halves. Now we compare the middle element with the key. So if we get a match, we return it. If we don't, we will choose which half will be used as the next search space. If the key is smaller, then the left is used as the next search space, and if the key is larger, then the right side is used as the next search space. We continue this until the key is found or the total search space has been exhausted. Now let's look at the algorithm. This is the algorithm for binary search. We have left equal to 0, right equal to n minus 1, which is the last index, and we have another integer middle. We start a while loop where left is lesser than right. We find the middle element uh, using the formula mid is equal to L plus R by 2. Again, we have three cases here. The first case is when the search element and the uh, middle element here are equal. So we do element equal to array of middle. If this is true, we return middle. Otherwise, we'll see if the element is smaller, then we set the right to mid minus 1. So we'll be dealing with only the left searching space. The left will remain 0, and the right will be set to mid minus 1. And then this process will be continued. Otherwise, if we have the element, like the searching element, to be greater than the middle element, we'll set left to be middle plus 1. So we move to the right searching space. The right will remain the last element of the array. Left will be set to mid plus 1, and the right searching space um, will continue this loop. This will be continued until left is lesser than right. And then when we get the element in the iterations, we'll be returning the middle. Like the element will be the mid during that iteration, and we use the return mid to get the element. This is the algorithm for binary search. We have this example here. We have an array again of size 6, and here now the key is 5. So first what we do is we have left 0, right is n minus 1 as we saw in the algorithm, where n is 6, so right should be 5. First we check if L is lesser than R, which is 0 lesser than 5. We move on, we find mid, which is equal to 0 plus 5 by 2, which is 5 by 2, we get the floor value 2. So doing the floor division, we have got the value of mid to be 2. Now A of 2 is 3. So our middle value is 3 in the array. Now we check if the element is equal to A of 2. So our element is 5 and A of 2 is 3. So we have 5 not equal to 3. Hence we move on to the next case. Here we have element lesser than A of mid. So 5 lesser than 3, which is again not true. So then we go to the last case, else. Here we this means that the element is greater than middle element, which is true. 5 is greater than 3. So now we set the left to be middle plus 1. So now left is 2 plus 1, 3. Right is 5. So now we're dealing with this part of the array, the right part. Again, we find the mid. Like we've finished an iteration, we go back here, we check if left is lesser than right, which is true. So we find the mid again. We get 3 plus 5 by 2, which is 4. Our mid now uh, is 4. So A of mid is 5. 5 is our required element. So hence we found the required element in the second iteration here. So we return mid, which is we return the index of 5, 4. So binary search is faster than linear search. Linear search goes through the entire array sequentially. In binary search, we use the divide and conquer. It is much faster than linear search, and it is very effective for large algorithms where linear search fails to work. It's more efficient than other searching algorithms with a similar time complexity, and it's well suited for searching large data sets that are stored in external memory. Like if the data set is stored on a hard drive or in the cloud, binary search is the most efficient and well suited searching algorithm for such cases. Binary search can also have certain drawbacks. The array should be sorted. It is one of the requirements of binary search. So it does not work on unsorted arrays. And the data structures that are being searched should be stored in contiguous memory locations for a binary search to work. This is another requirement. And the elements in the array must be able to be ordered. Like the elements of the array should be comparable for binary search to work. Now let's look at some of the applications of binary search. Binary search is used as a building block for more complex algorithms or algorithms used in machine learning, such as algorithms for training neural networks or finding the optimal hyperparameters for a model. Binary search is used for searching in computer graphics, such as algorithms for ray tracing and texture mapping as well. This is one of the major applications of binary search, and it is also used for searching a database. So such large data sets can also be uh, searched using binary search. It is one of the most widely used searching algorithms. So this was all the information on binary search. Now let's move on to the next and last searching algorithm we have, ternary search. Ternary search is another searching algorithm which uses divide and conquer method. It is very similar to binary search and it works only on sorted arrays. But here the array is divided into three divisions and the search is performed in the division containing them. So ternary search is very similar to binary search, where we use the divide and conquer method. And this algorithm also only works on sorted arrays. We need the array to be the sorted fashion. But unlike binary search, where we divide the array into two parts and then reduce the searching space based on where the element is present, here we divide the array into three divisions. Again, we reduce the searching space based on where the element is present, but here it is more precise because we have three divisions. So let's look at the working of ternary search. We use the index of the first and last element to calculate mid1 and mid2. So using this, we divide the array into roughly three equal parts. If the element is smaller than mid1, we search in the first subarray. If it's greater than mid2, we search in the third subarray. Otherwise, we continue the search in the second subarray. And we continue until the search element is found or subarray becomes empty. Let me explain this in detail. So firstly, we begin with a sorted array. We'll have two pointers left and right, pointing to the first and last elements of the array. So now to divide the array into the three equal parts, we calculate two midpoints, mid1 and mid2. Mid1 will be calculated using the formula left is equal to right minus left by 3. And mid2 will be done using right minus left by 3. So basically what we're doing is right minus left by 3. So mid1 is is going to be in the to the left of the actual like middle of the array. So if we're going to do left plus right minus left by 3, and mid 2 will be towards the end. So we do right minus left minus right minus left by 3. So now we've effectively divided the array into three subarrays. We can call them array 1, 2, and 3. So array 1 will be from left to mid 1, array 2 will be from mid 1 to mid 2, and the third array will be from mid 2 to right. So now to compare and find the search element, let's call the search element the key. So first what we do is we check if the key is equal to mid 1, and then if it is, then we return mid 1. Or next we check if the key is equal to mid 2, the value the element at mid 2. If that is true, we return mid 2. If the target or the key is less than the element at mid 1, we check if the key is less than a of mid 1, then we update the right pointer, we update right to mid 1 minus 1. So now we'll be moving the search space to left to mid 1 minus 1, the left side of the array, leftmost side minus 1. If the key is greater than the element at mid 2, we go into the rightmost part. If it is greater than the element at mid 2, then we'll update left to mid 2 plus 1. Again, the search space is now shifted to the rightmost part. So now the search space becomes mid 2 plus 1 and right. This is the array now we'll be continuing with if the key is greater than the element of mid 2. If none of these is true, this means that the key is between elements at mid 1 and mid 2. So now we have to update both the left and right uh, so that we get the middle array. We update the right as mid 2 minus 1 and the left as mid 1 plus 1. So now the array will be mid 1 plus 1 to mid 2 minus 1. Will be the middle array. And now this will be our search space and we continue this way. So we'll be repeating this process with the reduced search space until the key is found or until the search space becomes empty. If the search space is empty, then the key is not found. And then we'll either have a statement saying that the key is not found or we return zero. This is the algorithm used for ternary search. First, we check if right is greater than or equal to L, and then we calculate mid 1 and mid 2. Mid 1, as I already said, is left plus right minus left by 3. Mid 2 is right minus left by 3. In this way, we can calculate left and right. Then we have our 5 cases. The first case is where we have the key at mid 1, second at mid 2, third at the left side, fourth at the right side, and the last case, else case, is the mid part. So the first case where the key is at mid 1, we'll check if array of mid 1 is equal to key, and then if it is true, then we return mid 1. And then next we go to array of mid 2 equal to key. If that is true, we return mid 2. Now we check if the key is lesser than the element at mid 1. We go to the left subspace. This is a recursive call. We'll have right left to be L, right to be mid 1 minus 1, and key and the array remain the same. So now we move to the leftmost part of the array. Our search space has moved to left. The next is else if. We use the else if here. If the key is greater than the mid 2 element, we again use the recursive call and we update left to be mid 2 plus 1, right remains R, and the key and array are the same again. So in this call, like we'll be moving our search space to the rightmost part of the array. Our final case is when neither of these conditions are satisfied. This means that the key is in the middle part of the array. So this time we'll update both left and right in the recursive call. We'll update left to be mid 1 plus 1 and right to be mid 1 minus 1. Key and the array are again the same. So this way, using the recursive call, we can find the search element. We also have a return zero statement, which is implemented when none of the elements are found. This code can also actually be written using a loop and no recursive calls. I just use recursive call method. So this is the algorithm for ternary search. Let's consider this example. We have this array of size 30. So our first element's index is 0, hence our left is 0. Last element's index is 12, our right is 12. Basically, right is n minus 1, 13 minus 1 is 12. So the key here we're looking for is 10. 10 is stated as at index 2. So we'll see how we find this element. Firstly, we have right greater than left, which is true. 12 is greater than 0. So now we calculate mid 1 and mid 2. Mid 1 is L plus R minus L by 3. So we have 0 plus 12 minus 0, which is 12 by 3. So 0 plus 4, we have mid 1 to be 4. Next, we have mid 2, R minus L by 3. We have 12 minus 0, which is 12 by 3. So we have 12 minus 4, which is 8. So our mid 2 is 8. So 0 is L, 4 is mid 1, 8 is mid 2, and 12 is R. So we have divided the array into 1, 2, and 3 parts. left to mid one to mid two, and mid two to right. These are the three parts we divide the array in. So first we'll check if the element is at mid one. So we'll see if array of mid one is equal to the key. The array of A of mid one is A of 4, which is 13. 13 is not equal to 10. So we move on to our next, which is mid 2. We check if A of mid 2 is equal to the key. A of mid 2 is 27. A of 8, which is not equal to 10. So this is also not satisfied. So we've checked the first two conditions, which are not true. So now we check this condition where key is lesser than A of mid 1. 10 lesser than A of mid 1, which is 13. So 10 lesser than 13 is true. So we'll go to the recursive call where we update R to be mid 1 minus 1. So we've updated R to be mid 1 minus 1. So 4 minus 1 is 3. So now our R is 3 here and L is still 0. So now this is the array we'll be working on. 0 to 3. 1, 4, 10, 12 is the array we'll be working on to find the element 10. So I've taken that array separately here. Now our left is 0 and right is 3. Again, we calculate mid 1, mid 2. We obviously have right greater than left, 3 greater than 0. So we move on and calculate mid 1 and mid 2. Mid 1 is left plus right minus left by 3, which is 0 plus 3 minus 0 by 3. 3 by 3 is 1. 0 plus 1 is 1. So we have mid 1 to be 1. So this one. So our mid 1 is 1. Then we calculate mid 2. Mid 2 is right minus left by 3. So 3 minus 0 by 3, which is 3 minus 3 by 3. 3 minus 1 is 2. So we have calculated mid 2 to be equal to 2. So again, we've calculated mid 1 and mid 2. We'll check for first these two conditions, then we'll move on to the next three conditions. Checking for mid 1 and then mid 2. So A of mid 1, which is equal to A of 1, 4, which is not equal to key. So 4 is not equal to 10. We move on to the next one. A of mid 2, which is A of 2, 10 equal to 10, which is true. So A of mid 2 is equal to the key, and hence this condition has been satisfied and we'll return mid 2. So we'll be returning to the index of your element. So I hope it's clear using this example. Uh, the algorithm of ternary search has been explained clearly. Now, let's just see some advantages of ternary search. So, ternary search has a time complexity of big O of 2 into log base 3n. This is more efficient than linear search and it is comparable to binary search as well. Ternary search fits really well with optimization problems and is widely used in that field. Ternary search can also find maxima and or minima for unimodal functions where we cannot use binary search. But we also have certain disadvantages to ternary search. It is obviously only applicable to ordered lists and cannot be used on unordered or non-linear data sets. Just like binary search, we need the data set to be ordered or sorted. So ternary search cannot be applied on unordered lists. We saw that for unimodal functions, ternary search is more effective, but for monotonic functions, ternary search takes more time to find the maxima and minima of monotonic functions as compared to binary search. Binary search has takes a lesser time, and ternary search can be used more efficiently for the same operation. When we can use ternary search? So when you have a large ordered array or a list, and you need to find the position of a specific value, this is where ternary search is most effective. It uses the divide and conquer method. So if you have large arrays as well, it is very easily used there. For a function, if you need to find the minimum or maximum value, you can use ternary search as well. Ternary search actually can also be used when you have to evaluate a quadratic expression. So, summarizing what I've said till now, ternary search is the divide and conquer algorithm. It's used to find the position of a specific value in a given array or a list. And the array or the list should be ordered. It has to be in a sequential manner, it has to be linear. So the working is by dividing the array into three parts and we recursively perform the search operation until we find the dividable. I've used the recursive call. This can also be done using the loop. The algorithm has a time complexity of big O of 2 into log base 3n. It's more efficient than linear search. But actually, binary search is more widely used than ternary search, though it has a comparable time complexity to ternary search. And yeah, I think that's it. I've covered everything there. So these were the three searching algorithms we looked at: linear search, binary search, and ternary search. Linear search is a sequential search, and binary and uh, ternary search are interval searches. The most widely used searching algorithm is binary search, and it uses the divide and conquer method, same like ternary search. Ternary search is very similar to binary search, but it's just that it divides the array into three parts, which is why it is used more in large data sets where you can get the desired search element faster. So that was it about searching algorithms. Um, I hope I was informative and this helped you in some way. Thank you so much.